Hello, how about we take a look at exponential growth and decay today. We're going to take a look at growth first, and then we'll deal with decay. Remember, anything that displays exponential growth is growing at a rate that is proportional to how big it already is. So once it gets bigger, it grows even faster. When we're dealing with problems that might have exponential growth, you're always looking for if it's growing, if it says a growth rate or it's increasing or decreasing by a percentage. That's why this problem is going to have exponential growth. Let's read it. The prize for a radio station contest begins with a $100 gift card. Once a day, a name is announced. The person has 15 minutes to call, or the prize increases by 2.5% for the next day. How much will the gift card be worth if no one wins after 10 days? Notice here, the prize increases by 2.5%. So that $100 gift card increases by 2.5% the next day. Percentage relies on how big the thing is. So $100 increased by 2.5% is $102.50. Increase that again by 2.5%, and you're not just tacking on $250. This time you're tacking on about $255. Increase it again, and you're tacking on about $262. So how much you're adding each time gets more and more. That's exponential growth. How much will the gift card be worth if no one wins after 10 days? Well, we don't want to go through this and do it 10 times. We could slowly, but instead we're going to rely on our nice exponential growth formula here. Y equals A times 1 plus R to the T power. A, that's your initial amount. What do you start with? What's growing? And then it's 1 plus R, your rate. Typically a percentage. However, when you do the formula, you have to use decimal. You have to use the decimal form of your percentage. And T is time. How many years, how many days, how many minutes? It kind of depends on the problem, but it's your time, your unit of time that the problem deals with. Let's set up this problem. How much will the gift card be worth? Y equals A, our initial amount. Well, it's a $100 gift card. So 100 times 1 plus R, which is our rate of 2.5%. As a decimal, move the decimal point left 2 spots. So it's 0.025 to the T power. That's the base equation. Now, after 10 days, it'll be 100 times 1.025 to the 10th power. This gives us 100 times 1.28, I rounded my decimal, and then times 100 will be 128. So how much will it be worth? $128. I want to point out that this A out front, it's not super arbitrary what it's doing there. Like, why is it the initial amount? Because think about our equation down here for our example. When T is equal to 0, let my T be 0. Anything to the 0th power is 1, right? So that means all of this goes to 1, and I have 100 times 1 is equal to 100. When is T equal to 0? Right at that start, when I have that $100 gift card. So it makes sense that when I put into my formula a 0 at the start, it outputs 100, as it should. Going over, the problem of exponential decay. Our exponential decay function, remember, that's something that decreases at exponential amount. So it may be every set time interval it gets decreased by half or a third or maybe 1/10. The only difference in our formula here is that it's 1 minus R. So if you ever have a function telling you that something is decreasing or losing something at a percentage, that's exponential decay. If you lose an amount according to a percentage, exponential decay. If you gain something by an amount, exponential growth. And it makes sense that we have a minus because we're decreasing, so let's subtract that rate at which we're decreasing. In the other problem, we're gaining something at a rate, so let's add that. So that minus sign is our only difference. Problem. A fully inflated child's raft for a pool is losing 6.6% of its air every day. I don't know who's measuring that, how they're measuring that, why on earth they're measuring that, but they are measuring that. The raft originally contained 4,500 cubic inches of air. That's how much volume of air was in that raft. How much air will be left in the raft after 10 days? Well, it is exponential something, because I see that percentage. It's gaining or losing something by a percentage. And then even further, I'm losing air. I'm decreasing by a percentage. That's exponential decay, guys. So I have to set up my formula. Y is equal to A, our initial amount. What are we talking about? We're talking about air. How much air is in that raft? How much air is in it at the start? 4,500. Times 1 minus our rate, 0.066. Remember, we need decimal form of our percentage, to the 7th power, because I want to know after 7 days. Notice how t is in days here, because my rate is given every day, and then it says after 7 days. So in this problem, in this context, days is our unit of time. So this will become 4,500 times 1 minus 0.066 to get 0.934 to the 7th power. Do some nifty calculator work, raise that to the 7th power, and then multiply by 4,500 to get 2,790.23. I'll round it there. Cubic inches of air. Notice our amount of air is less than what we started with. That's good. It sure better be, because it said we're leaking air. We're losing air at that rate. So 2,790. Example of exponential decay. The only difference between exponential decay and growth, as far as the formulas go, is that minus or plus. And it matches up with what you'd intuitively think. As my rate decreases, it's going to be minus r. If it's exponential growth and I'm increasing by a rate, I will go plus that r.